This is Team 16's proposal for the Interstellar Exploration mission. The objective of our mission is to send a 50-kilogram scientific payload to the interstellar space within 20 years or less, and to send back data to Earth for an additional 20 years after crossing the heliosphere border. Similar missions to this have been, of course, Voyager and New Horizons. Why is this important? Our knowledge of the heliosphere and interstellar medium is incomplete, so a dedicated mission to this area is ideal. Our stakeholder, of course, will be NASA. Financial projections are based off of course, Voyager and New Horizons, placing our mission in the $900 million ballpark. Funding will be supplied by, of course, NASA, Roscosmos, and ESA. The CONOPS for our mission is as follows, with a launch, ejection burn, gravitational assist burn around Earth, as well as other planets, followed by an interplanetary cruise and interstellar cruise. Each subsystem of the probe has a critical event in the CONOPS where it is most needed. For example, the structure of the probe is most critical at launch. The probe's onboard propulsion is most critical during gravitational assist burns. Our probe requirements follow directly from the mission requirements in that our power generation system must operate for both the 20-year cruise to the heliosphere and the 20-year cruise after we pass the heliosphere. In addition, it must provide sufficient power to both communications and the scientific instruments for the 20-year cruise, as well as carry at least 20 kilograms of scientific payload, as well as collect, store, and process the data from the payload and send it back to NASA for at least 20 years after escaping the heliosphere. Finally, the probe must be able to execute maneuvers and autonomously navigate in the event of a communication failure, which is extremely likely considering the distances involved. The decomposition of our probe is as follows, with our launch through interstellar cruise travel section to our data collection to the termination of the mission. The morphological matrix helped us to characterize our probe as well as the launch vehicle. We determined that aluminum was the ideal material for the majority of the probe, with one exception being that carbon fiber will be used for hardpoint attachments on the outer hull of the probe. The N2 diagram describes how commands get sent from mission control to the probe and to the rest of its subsystems. In general, commands from mission control propagate all the way down through all subsystems, which are then filtered back through the onboard computer, which are then transmitted back to mission control to repeat the process. Following trade studies were used to better characterize which materials and technologies we would use for our probe. For instance, for the structural material, it was found, just based off qualitative estimates mixed with some quantitative values, that carbon fiber was the best. However, because that has never been used before, we went with the next best option, aluminum, for the majority of the probe. However, carbon fiber will be used again for the mounting points. For propulsion, it was found that the ion engine would be ideal, with plasma engines in a close second, followed by traditional chemical liquid-fueled rockets.
Hello, I'm Simeon Salia, and I will be dealing with the launch propulsion, in-space propulsion, trajectory corrections, the power system, and the altitude control. For launch, the Atlas V 500 series will be used. It is capable of putting the probe directly into Earth and space solar escape trajectory with a velocity of 16.26 kilometers per second. The initial velocity will assist in the requirement of the probe to make it to interstellar space within 20 years. Then the next T is an ion propulsion engine, which will be continuously running during operations. The thruster will be running at approximately 75 millinewtons. of thrust, and only 2 of them will be running at any given time. The power consumption will be 1.5 kilonewtons. The next C's lifetime is approximately 5.5 years, running at a max thrust of 237 millinewtons. Altitude control will be handled by the MR-401 hydrazine rocket engine. While in operation, it will produce 0.09 newtons of thrust, and it will be used to handle spin up and spin down maneuvers as well. Trajectory corrections will be done by the MR-103J. It has an output thrust of 1 newton and is capable of handling emergency maneuvers. It is also capable of working autonomously in case of emergency. The power source of the probe will be a general-purpose heat source, radioisotope thermoelectric generator. It is capable of generating 1.8 kilowatts of power using 6 units running off of 7.8 kilograms of plutonium-238.
The structure of the probe is summarized in the following slides. We went with an aluminum alloy and carbon fiber combination based off of our trade study and based off of the legacy example of New Horizons. Aluminum alloy honeycomb structures offer a high-strength, low-weight alternative, and they provide excellent electromagnetic shielding to protect the electronics on the probe. Furthermore, the thermal control system on the probe is composed of a Dacron mesh, Mylar, and Kapton film, which have largely remained the same since the time of Voyager and New Horizons. We're trying not to reinvent the wheel. As for the scientific payload, we are borrowing from Voyager, extracting the interstellar scientific instruments only, neglecting the planetary science ones. This list is what remained. We have an imaging science system, which is in essence a camera, the ultraviolet spectrometer, the magnetometer, the plasma spectrometer to get a better idea of the structure of interstellar space, a cosmic ray telescope, and the radio telescope science system.
Hi, I'm Yuga Ojima. I'm basically in charge of the software part of the project. Now I'm going to talk about the Integrated Electronics Module, or IEM. So what is IEM? IEM is a space and weight-saving device which is a single box containing command and data handling processor, guidance and control processor, data recorder, and so on. We also going to have a redundant IEM as a backpack just in case, because there is a possibility to encounter systematic problem during the flight. So there are 2 major components of IEM, which are processor and recorder. Processor is like a human brain, and recorder is like data storage. And there are some details here, but I'm going to skip it for now. Next, I'm going to talk about accurate ranging. The characteristics of the ranging system is that it uses onboard regenerative ranging to track distance between the spacecraft and Earth. And there are 2 major ranging systems, which are normal ranging and regenerative ranging. Normal ranging amplifies and sends noisy tone back to Earth so that it adds errors to range measurement. On the other hand, regenerative ranging regenerates tones without noise. Therefore, ground stations can receive much clearer signals and more accurate ranging. Therefore, it improves spacecraft guidance. Next topic is communication system. The communication systems depends on ground stations, the deep space network, laser communications relay demonstration, and the spacecraft's receiver. The important parameters here are bandwidth and data rates. If we have higher bandwidth, meaning we're going to have more data per second. But basically, radio waves are primarily used for the spacecraft. But here, for this project, we're going to use optical waves and lasers because we're going to have higher data rates by the wavelength. And data rates depends on spacecraft distance, power used for the transmitting data, and the size of the antenna on Earth. But basically, a higher bandwidth means higher data rates. Here we have a picture of the deep space network. So we're going to use a laser communications relay demonstration, or LCRD, which is basically optical and laser communications relay satellites. But why do we use this? Because optical waves have 10 to 100 times more bandwidth than radio waves, meaning that it packs data into tighter waves so that ground station can receive more data at once. That means faster communications. We're also going to have a smaller size so that we're going to have more room for scientific instruments, and lighter weight means being less expensive launch, and so on. But there is also a problem. The laser cannot penetrate the cloud coverage. But we also have a solution. We're going to have more choice for ground stations so that we will be more flexible to avoid weather interruptions. Yep, that's all about our interstellar exploration project. Thank you for watching.